So good morning, afternoon, evening, depending on where you are. Hey, hi Peter. Um, so tonight I want to continue working on the CPU cache I've been working on the past two streams. Um, Hopefully, I'll try to re-explain the basics so you can follow if you haven't seen the past two streams, but some things might not make sense. Don't hesitate to ask in the chat if you have any questions. What I wanted to start with tonight is first a couple of corrections of things I said in the past stream that turned out to be just either not entirely precise or just plain wrong. So the first thing is about the memories, the embedded memory blocks in the iCE40. So these things. I said that they were read before write. It turns out that they're not. At least according to the simulation model from Lattice, they are undefined. So you can't read and write at the same address at the same time. Like the write will succeed, but the write output will be invalid or unknown. So that's kind of an issue because if we take our schematic, where is it? Oh yeah, here. So in this pipeline, if we access the same cache line at consecutive cycles, well, we'll read and then we will write the update for that same cache line at the same cycle. So at least according to the simulation model, that would fail, and the read data that we would get here would be invalid. Now, in practice, I don't think the read data would be invalid. I'm pretty sure that it's either going to be the old data or the new data, one of the two, but it's not going to be just random crap. And if you use the inference from uses, as far as I know, it doesn't deal with conflicts or add any logic to protect against that. And pretty sure some people have used that successfully. Anyway, I still decided to deal with it properly and to not do that. And the way to avoid this is I'm just gonna do that here. Because those memories are very fast, like they can go probably more than 100 megahertz, and we're using them at very low speed in this particular design. So what I'm gonna do is basically, instead of having the read and write clock be the same, I'm gonna clock the right side on the negative edge. And so before I would have had something like this, where you have the memory with the write signals, and then you have the clock, writing to them. What I'm gonna do is, instead, the write signals, I'm gonna register them in a normal fabric flip-flops, and this is not gonna cost me any logic, because most of the write signal, they are combinatorial outputs, which mean they go through a LUT. And if they go through a lookup table in the FPGA, I immediately have a flip-flop next to it, which is basically lost if I don't use it. So I can add that register for free, basically. And then that registered version of the signal I'm gonna feed to the embedded block RAMs. And the embedded block RAMs, they have an option where you can basically invert the clock. And so that's basically what it's gonna look like. If we look at the data sheets here, Yeah, see here, the right clock, we have the option to invert it or not. And so by inverting it, what we're gonna do is that we're gonna read on one edge and write on the other, which means we don't actually have any read-write conflicts. And then we can avoid the problem altogether. So that's the first correction that I wanted to say. The other is that I was kind of complaining that if I wanted a larger memory, Yosis was doing something weird. Instead of just configuring the RAM into these RAMs you can select if they are 16-bit wide or 8-bit wide, and Yosis wasn't using that mode, and I was kind of complaining. I was like, okay, why doesn't it do that? And the reason is here. No mask port. So it turns out that the mask port that I use in my design to only write some of the bits, so that I don't update the tag, I only update the age or that kind of stuff. This mask port does not exist unless the memory is configured in 16-bit wide mode. And that's because internally, inside the FPGA itself, the memory is actually 16-bit wide, like all the time. And when you configure it as a 8-bit mode, if you want, it internally uses the mask port to only write 8 of the bits at a time. And so the mask port is used kind of by the logic that changes the bit width, which means it's not available for you. Now, that doesn't mean that we can't still sort of use it, but what you need to do is configure the read side to be 8-bit wide, and you keep the write side being 16-bit wide. You duplicate the bits, at the right place, and you generate the mask port yourself. So you basically all the logic that the FPGA has internally to allow changing the write side from 16-bit to 8-bit to 4-bit to 2 bits. You basically duplicate that yourself and re-implement it in logic. Piotr, I added the overlay. It doesn't really work super well over like in over white background. I'd like to put like a small opaque thing, like a half transparent or something, but I couldn't figure it out like in the 2 minutes that I looked at. And so that's actually something I've done. If I wait, where do I have this? So I actually implemented iCE40 EBR, like an embedded block RAM wrapper, which kind of makes it more, makes it easier to use instead of using the raw primitives, you can use this, and this is a little more convenient. And it's gonna do really like all the bit magic and basically placing the bits at the right place and all that kind of stuff. Because if you look at the embedded block RAMs, like the actual documentation, I don't know if it's written somewhere. But when you're not using the 16-bit wide mode, when you try to use the other smaller width, which bits you need to actually use is very non-intuitive. Like it's not bits, like if you want the 4-bit mode, you're not gonna take bit 3, 2, 1 and 0. It's gonna be like a bit 11 and I don't remember the exact number, but it's like some weird combination. just due to the way where it's implemented internally. I think it's not actually even documented in the datasheet. You have to read the simulation model to figure that out. But anyway, yeah, I wrote that wrapper to make things a little easier. Yeah, I didn't want to spend too much time on the streaming setup. Still want to do a couple of things, but for now that will do. So what else did I want to mention? So yeah, that's pretty much all the kind of quirks of the embedded block RAM of the iCE40 that I've dealt with. The other thing was, like on stream last time, I realized that the formula, that the way I was computing the how to modify the cache line age, so update the age was completely wrong. Hey, hi Matthew, welcome to the stream. And so I figured out how to actually update the age, and that's actually not very complicated. Basically, if you imagine that this is the age and this is the way, so this is way number 0, number 1, number 2, and number 3. Let's say that the least recently used age is well, let's just take 0, 1, 2, 3, it doesn't matter. So this way number 3 is the one that's currently is the oldest one, right? Now assume that we have a hit and we access way number 2. So this way is being accessed. What is the next age that we must compute? Well, where we have a hit, it's obviously 0 because it's the most recently accessed, because well, we just had a hit on it, so obviously. And then every age that was larger than 2, which is the previous age of where we have the hit, stays the same, and all the other one are incremented by 1. And then we have more updates. So that's basically the logic, is that the next age is 0 where we have the hit. It's the previous age if the old age is superior, is larger than the hit age, and else it's old age plus 1. That's how you compute. Now, the annoying part in this is that the hit age, that's actually something pretty complicated to compute. I mean, you need to know which way has the hit, and then you need to mux and fetch the correct age for that way. So that's already a significant amount of logic, and it turns out that this actually becomes the critical part. I mean, there is still plenty of margin there, but that's something that I failed to see in my first evaluation. But thankfully, it doesn't have any impact. But that's sometimes the kind of thing that can kill your design and ruin everything. If suddenly you realize that, okay, something that I thought I could compute quickly, I can't, and this becomes my critical path and kill my Fmax, then you might need significant change to your design. Thankfully here it's not the case. So I think that's pretty much it for all the comments about the previous stream. Something I'd like to mention though is that, I was looking at the logic and how Yosis did some stuff. And sometimes, it seems like it's really dumb. But some of the times it's like really clever. Like just this afternoon, I was looking at how do you implement like a 4-to-1 mux. Let me just clear this page. So the usual way I used to see 4-to-1 mux. So basically this, right? You have two select signal, and then you have signal 0, signal 1, signal 2, signal 3. You want to do output, and you select it with a selection signal. Okay. How do you implement that in LUT4? The way I used to think about it is basically this. S2, S3, and so something like this. And so this would be a LUT4, this would be a LUT4, this would be a LUT4. So this would take 3 LUT4 and 2 layers of logic. Now obviously this is 3 LUTs per bit that you need to mux. Like imagine that you want to mux 32-bit signals, which means you'd have 3 times 32 bits LUTs, which would be 96 LUTs. Obviously for a 1-bit signal, optimizing that doesn't matter, but often you need to mux like very wide bus. Like if you have like 5 peripheral or 8 peripheral on your wishbone bus, on the read data side, you basically need a 8-to-1 mux, and so that would be 2 of those 4-to-1 mux plus 1 2-to-1 mux. So that the number of LUTs can rise pretty quickly, which means that optimizing this unit is pretty important. So that's the way I used to think about them. And this afternoon I was asking Yosis to synthesize a 4-to-1 mux, and I had trouble making sense of the logic it was generating. It turned out that really does something pretty clever. Instead of implementing it like that, what it does is it has this mux with S0, S1. And it also inputs both selection signal to it, cell 0, cell 1. And the first LUT, it configures it to output either S0 or S1 or cell 1 or cell 0, sorry. So basically this is either S0, S1 or cell 0. And then using a second LUT, it muxes S2, S3, like this. So if you look at this, in theory, here you're already using the 4 inputs of your LUTs. Like you're using this input, this 1, 2, 3. You have 4 inputs, and so you can't control that mux. But the thing is that mux is only used if this input isn't used. And so that's actually a pretty clever errand, like a way to make things. You still have two layers of logic, which means you haven't increased your logic depth or lengthened your critical path, but now your 4 to 1 mux is done in just 2 LUTs per bit, which means that if you had a 32 bit mux, you only need 64 LUTs, and you just won 32 LUTs just doing this. I thought that was a pretty nice trick, and I had never seen it before. Maybe it's super common and I just missed it all this time, but yeah. Anyway, that was just a small tangent that sometimes uses this dumb things that you can easily do better yourself manually, but sometimes it does really clever things that I didn't think of. So it's always worth trying, both approach and see what works better for your particular case, because it's kind of hard to predict. Okay, so let's move on to have a quick look at what I did since the last stream. So I didn't design anything new. All the design part I thought I would keep for the stream, because I think that's the most interesting part. But I did, write down some Verilog that actually implements stuff that we designed on the 2 previous streams. As I already mentioned, I wrote like the embedded block-RAM wrapper that just handles a bit of bit shuffling and stuff like that, just really annoying stuff, but that just makes it way more convenient to instantiate those block RAMs. I wrote this, which is kind of the equivalent, but for the single port RAMs. So the single port RAM, this just can't infer them at all, so which means you need to instantiate them. And so doing it manually can sometimes be annoying. And so here I just made a quick wrapper where you just, say how many address bits you want, say the data width you want, and it will generate an array of those single port RAM that match whatever you want. And yes, Matthew, this is stream number 3. Sorry. Yeah, the stream number 2 I kind of did like spontaneously, like without much warning, and I think it was kind of middle of the night for the US, just because I wanted to work on it and I wanted it to be recorded, and so yeah, I ended up streaming very early. I think it was like 6 a.m. in the US. Yeah, but the stream is recorded. You can view it on Twitch, and you can view it on YouTube as well. So what I did on stream number 2 is basically take a very kind of deep look at Yosys synthesis and stuff like that. It's actually stuff that you did on your own stream, so it's pretty much all stuff that you know. It's like, using the LTP command and using the show command to inspect the Yosys synthesis result and see, okay, that's the logic I would expect and that kind of stuff. Like drawing on paper the kind of logic that we want implemented, and looking that the Yosys results are actually consistent with that and are not, massively have not massively longer critical path or stuff like that. So yeah, so that's just a wrapper for the SPRAM. Again, there's really nothing too interesting here. It's really just bit shuffling and stuff like that. So yeah, and I mean, the kind of arrays that you can generate for the SPRAM is kind of limited because you only have 4 of them, right? So you literally you can only generate like a 2 by 2 array, a 2 by 1, a 1 by 2, or a 4 by 1, or a 1 by 4. So that's, you get like 6 possible configuration, which is really, I know, which is really not that much. One thing to know though about the single port RAM that will become kind of relevant later is that here I put a read enable port. They don't really have a read enable port. Like if we look at the documentation, where is the documentation for this? If we look at the port list, there's a write enable, there's no read enable. There's a chip select, and that's what basically I'm using as a read enable. So first, okay, why read enable is useful is if you don't want the read data to change even if the address changes. So imagine imagine this is the address port and you're inputting address 0, address 1, address 2, address 3, and let's say that this is your read enable. And this is the data out. What you would expect is something like this. So that's just invalid, that's invalid. Then here you get data 0. And here, because read enable is low at this cycle, the data wouldn't change and would stay D0. And here we would have data 2 and then data 3. And that's kind of useful if you want. Oh, I'm sorry. Yeah, I sometimes forget to switch the scene. So that's the address line, okay, and that's the read enable line, and that's the data out line. And so what happens is that on this cycle, because read enable is high, the data switches to D0 because we do a read. But at this cycle, because read enable is low, the data remains stable and continues to output D0. And then here we again have read enable set to 1, which means that we do execute a read on address 2 and we output address 2. And that's useful when you want to execute a read pipeline, something like this, where you have a counter. So this is just an increment by 1. So that's just a counter. And you want to output data to some other block, and that other block provides you with a ready signal. And so that ready signal, typically you would use it to drive the clock enable of that register and the read enable of the RAM. Because basically what this allows you to do is, here you have like a read pipeline, a 2-stage read pipeline, because you have this register and this register, and you want to, when the receiver is not ready, you want to halt the entire pipeline, but you need to keep the data out stable while the ready signal is not present. If you don't have a read enable, there are 2 ways that you can deal with that. Is let's imagine you have a RAM that doesn't have a read enable, that happens. And then any change at the address input will result in a change in the output. The way to deal with that is basically have the register like this. So that's one way to do it, is that basically instead of gating the clock enable of this or the RAM, you use the ready signal to increment or not the counter. The downside of this is that this ready signal, now you have a combinatorial path that comes from here, goes through an adder, and then to the RAM input. And so that's actually a fairly long combinatorial path, which can limit your maximum frequency. While if you look here, that's a register output, that's a register input, it's like super fast, and both of these are direct register input. That's a clock enable directly, and that's a read enable directly. There is no combinatorial logic at all. So this would run much faster than this. But if you don't have a read enable, there is not much that you can do. The other option is you can add what's called a skid buffer, where basically you have this, you have your counter with the register and everything, and then at the output, let me so the other option, if you don't have the read enable here, is to have a skid buffer. So basically what you do is you save the value that you're gonna lose because you don't have a read enable. You basically need to save it in a register, and then have a mux here that either gonna take the value that you saved or the new value, and then here you have a bit of control logic just to drop that mux. So that's basically the three way to do a read pipeline. My preferred one is this one because it's often the fastest, just because it's direct register input everywhere, but that means you need a read enable. On the SPRAM, I'm kind of hoping that the chip select will act like that. I will need to check that and possibly even check it in hardware, check the simulation model and check in hardware to make sure that it actually does that, because it's not really clear at all in the datasheet what it does. But if it doesn't, I'll basically probably fall back to this model. I mean, yeah, both model. This one, the advantage is that you increase the critical path in your data out slightly because you now have an additional mux, but it does cost you, a mux here and a register here, which is pretty high. If your data out is like 32 bits, this will just cost you like 64 LCs like instantly. Which, when your entire logic, I'm targeting something like around 300 LUTs for the entire memory cache. So, paying 64 LUTs just for the skid buffer is it's kind of a steep price. And the inconvenient here is that the register here can no longer be packed with the other in the same LCs, because you use the output of the combinatory logic both to drive the register and to output to some other logic. And in the iCE40, that's something you can't do. On some FPGA you can, like Xilinx. I think the CP5 can as well, but the iCE40 you just can't do that. So, and since this is the iCE40 target. Okay, so that was the SPRAM wrapper. Let me go back to the other things I've done. I have two. Yeah, that's an old file. So the taggram is really just again a block that's mostly shuffling bits around, and it uses this iCE40 EBR primitive to instantiate the block RAMs depending on how many it needs, and it provides a nice interface with the signal that are named and everything. That's actually just a cleanup of what we did on stream last time. Same thing for tag match. So tag match, it's essentially a manual implementation of the comparator. Because I wanted to be able to compare manually creating the LUTs and letting users do everything, I implemented partly manually. And I have a if-def select where I can switch between the two implementations to compare the results. And we'll see at the end how it turns out or not. It's definitely not always worth to do it, especially this early, because most of the time you can just try out things without doing it. But here I kind of wanted to use this stream to kind of evaluate both possibilities, and so I did it already because I knew I would do it anyway. So. And then I wrote MC Core, and so MC Core is basically the start of the implementation of the logic that we designed. So if we go back to what we designed to the first stream, is basically the implementation, the start of the implementation of this thing. I really have not coded any of the logic. The only logic that's implemented in here is, well, first, selecting the right parameters, like the width in bits of various fields depending on the cache configuration that you set here. So you can actually dynamically select how many ways you want, how many, what's the size of your address space. So here we have up to 64 megabytes. The cache line size you want and the cache size that you want, 64 or 128K, and it will compute all the fields dynamically, and even print you a little report about the cache configuration. All the signals here and everything. That's what we did in the last stream. I just integrated them in this file and renamed it a little. I did add the beginning of a state machine for the control, but it's not implemented yet. It's just the kind of the skeleton implementation with Verilog. There is no code that does anything, and the rest is all of this stuff. That's the logic that we did last time. I just added some comments and organized it, and that's about it. I did add this, which we didn't write last time. We designed it last time. We looked at every blocks in the logic. Where do we need muxes between bus access mode, where we're actually serving bus requests, and memory load load and store mode. So, you know, loading cache line and flushing cache line to and from the main memory, where we will need muxes. We are gonna look at that. Yeah, you know, that's what we wrote last time. And so if we look here, that's the SPRAM mux. Let me go there. And so here we see, okay, address between bus mode and mem mode. Okay, that's the address for bus mode. And so, yeah, we have, you know, hitway and then request address index and request address offset. I mean, we renamed some of the signals, but they're the same one. And same thing for the write data, the write mask, the write enable, what they are and what they should be. That's what we designed last time. I just converted it to Verilog, but it's straightforward. There's basically no thinking involved here. And so now, finally, like 40 minutes in, we're finally gonna start onto the design part of what I wanted to do tonight, is designing the way we're gonna access external memory. Because all of this design, that's really just serving bus requests. So that's like fetching data, letting the CPU write to the cache and read from the cache, but not actually exchanging any data between the cache and the memory, which is kind of what it needs to do, right? So how is that gonna work? We touched a little bit on it last stream when we, you know, said what muxes we needed, but that's about it. So I'm gonna try and explain what I'm thinking now. So let me just take a new page. Well, actually, yeah, that's actually something I mentioned on the first stream, on the very first stream. That was kind of what I was thinking at that time. You know, it's been slightly adapted, but that's basically what we need to do, right? Is we have a runtime mode, which I'm in all the streams I'm now calling actually bus mode, which is basically the cache is serving requests from the bus. And then while we have cache hits, we stay in bus mode all the time. And then when we have a miss, which means that the CPU wants to access something that we don't have in the cache, well, we need to load that from memory, and possibly, depending on what we decided to evict, if it turns out that what we need to evict, you know, make some space in the cache before we can load a new line. If the current line is both valid and dirty, which means that the CPU has written to it and we haven't flushed that to the main memory, we need to first flush it. And so I draw this kind of state diagram. Now, that's not the way it's gonna work. I mean, that's what it's gonna do, but that's not going to be the state of our state machines. And to understand that, I'm gonna draw the data path for loading and writing things from the memory interface. So let me take actually a new page. Okay. So let me think a second about this so that I'm not screwing up too much. So mainly we have so in this diagram I'm only going to draw the logic when we load and store data from the main memory. So all bus access, I'm not drawing them because the diagram would be too crowded. So you can assume that, you know, in front of the SPRAM, yeah, there is a mux and stuff like that, but I'm not writing it down here. So we're gonna start with the flush. So the flush is basically taking data that we have in the cache and sending it out to the memory interface. So the memory interface, let me see. I did explain it in the first stream, but maybe it would be useful to have a slight reminder. Let me just, I don't have the one for SPI written yet, but I do have the one for the iPRAM, which is the same kind of the same interface. So I'm just gonna open that file. Okay, so that's the memory interface. And so, as I explained, we have a control channel where we give an address, a length of burst if we want to read or write, and then we have a valid ready handshake. Forget about linear and CS, that's iPRAM specific, it doesn't matter here. And so we send basically, okay, I want to read that many words from that location in memory. And then we have a write data channel and a read data channel that are used to exchange data sort of asynchronously with the command, in the sense that the first thing you do is you send the command, that's the first step, and then at some point later in the future, for a read, the controller will provide data to you. You don't know when, you don't know the delay or that kind of stuff, because it's going to depend on the memory technology and if the RAM is busy for something else or whatever. But at some point you will get them. And you have a storm indication to tell you when you get each word. And for the write, it's kind of similar. You provide the data, and you must be always ready with the data. And the memory controller at some point will tell you, okay, give me the next one. Okay, give me the next one. Okay, give me the next one. And that's the acknowledge signal. So that's the way the memory interface works. It's sort of similar to AXI, but it's like heavily simplified, because yeah, AXI has much more flexible handshaking on the write and read data channels, which make things much more complicated. Here I simplified that, so it's much easier to implement. It's much harder to get wrong, basically. Oh, well, actually, I had already implemented the memory interface here. Yeah. So let's go back to this. So when we're flushing data, we're taking data to from the cache to the main memory, which means that the read data port of the SPRAM, we pretty much just send that directly to the mem interface write data channel. And of course we need to read those data, we need to read the correct data. And so look at this. One, and then here I have my clock enable, I have my read enable. That's exactly what I explained in, a few minutes ago. So, I mean, there was a reason I wanted to read enable on the SPRAM. It's exactly for this, right? Now the address is kind of split in different parts, and the only part that's actually counting up is the offset within a cache line. The rest is just fixed input, and that's just a register. So that's pretty much the data path when we're sending data from the cache to the memory controller. Now we have the other way around. We have the mem interface read data. This would go directly inside the write data port of our SPRAM. We need a write enable signal. Well, the write enable signal is going to be the memory interface read strobe. So basically every time the memory controller tells us that we have a valid data, we go and write to the RAM, and at the same time we go and we actually increment our counter as well, because we're just gonna reuse the same counter, right? It doesn't make sense to have a different counter. So here we will just have an OR gate and something like this. And we'll just have some reset control signal that resets our counter to 0 at the beginning of the command, whenever, basically. That's control signals. Usually I just leave them, I just don't draw them in the diagram because they have to be generated by some condition that I'm just gonna come up with when I actually write the Verilog. But in this time, when would we reset the counter is basically when would we reset the counter? When we issue the first Yeah, basically we would reset it on a miss. So when there's a cache miss, we know we're gonna do something with the memory operation. So we reset it on a cache miss, and because we know we're gonna need it. And when else would we reset it? We need to reset it when we're done flushing and when we go and when we when we're done flushing. So when we get the last ACK, when we get the right ACK last. Do you mostly just draw data paths? What level of detail is work going to? I start with the data path always, pretty much, because I draw stuff to get a better idea of what's gonna be the smallest, and usually data paths are wide, like they're 32 bits and stuff like that, which means that a small optimization can yield the most improvements. Right, like if I have a 32-bit wide data path and I manage to save 2 lots per bit, I've just saved 64 LCs like instantly. So I usually start by that, the data path. And in the data path, most of the control signal, I just don't really write how they're generated. I just set they are input, whatever. Then when I actually start writing the actual logic, there's going to be two cases. If they are really simple control signals, like they don't depend on the output of large comparators or stuff like this. Like I'm not comparing like big numbers or stuff like that, and it's just combining a few logic signal or testing if a FSM is in one state or another. I'm pretty confident that the logic optimizer is going to do its job correctly. Like I usually have in my head the for instance, like this reset counter. Okay, I say cache miss or write hack last. Okay, I know that the cache miss is the output of a register, which means I know it's going to be fast. And write hack last, I know it's two direct inputs from the memory controller, and so I need to combine basically the write hack, the write last signal, and the cache miss. That fits in like one LUT4. So intuitively I know, okay, that's gonna be super fast. I don't need to worry about it. If you go back as to what I discussed in the last stream, that was like a lot of combinatorial logic, like all of this. All the logic here that you have large wide comparators that compare like big numbers, a lot of them in parallel. So that can quickly grow in size, and so that's why I went into the detail of thinking, okay, that's the kind of structure I'm expecting. That's the way I'm gonna compute those signals. I mean, you can't read this entire, like this sheet is not gonna make much sense because it's like I was drawing and explaining at the same time, right? So you'd have to watch the stream to make sense of it. But here, because I knew that it was a lot of control signal, testing a lot of stuff, I knew this was gonna be my critical path, and so I went to much more detail. Like I draw lots and stuff like that to have an idea. Okay, how many layers of logic am I gonna have? That kind of stuff. So the level of detail I go into is basically heavily dependent on if I expect this to be a long logic path or not. Something I expect to be done in one or two layer of logic, I'm not gonna bother. At least for the control signals, because they're small signal, like 1 or 2 bit wide. For data path, I might go into much more detail. But if I expect, this logic is going to be 100 LUTs, which means there's possibly a lot of space for optimization, and it's 7 or 6 layer deep in the end, which is rather deep and stuff like that. Do you care more about? Yes, usually I care more about Fmax than the number of LUTs. I care about the depth of the logic tree. So if I can spend some LUT to shorten the depth of the logic tree, then I will most likely spend them, unless it's unreasonable. Like I'm not gonna spend 100 LUT to gain one layer, go from 8 to 7. That doesn't make sense, right? But if I have to spend 10 LUT to go from 8 layer to 7 layer, I'll do it absolutely. Now, some of the signals, they're generated into, some of those signals, it takes 7 layers, right? Some other signals, it takes 3 layers. I'm not gonna spend any LUT going from 3 to 2 if I have another pass that's 7 layer deep, right? Because that's not gonna change my Fmax. So I'm only willing to spend the LUTs to reduce the maximum length path and not the other ones, basically. That's kind of the idea. And that's for control signal. For the thing is, for data pass, a lot of the times reducing the number of LUTs is actually increasing your Fmax, because for those it's very common that if you manage to reduce the depth of the tree, you actually reduce the number of LUTs as well. So it's not always the case, but it often happens. It is. Okay, so that's pretty much the data path. You know, to exchange the data from the memory interface to the SPRAM. So it's really straightforward. It's basically a counter. Like, it's very simple. And of course, the other part of the memory interface is actually sending the commands, right? Because this only deals with the data. We actually need to provide the address where to read and write from memory. We need to provide the length. So providing the length is very easy because it's a constant. It's just the cache line size. So that's pretty straightforward. We need to provide the read-write signal, which means, okay, are we issuing a flush? Are we issuing a load? And what else do we need? If I take, so let's see, well, that's it. And then we just have the valid and ready, you know, handshake signal. And so that's pretty easy. And so if I come back to kind of the state diagram, yeah, that was it. This, the actual state that we're gonna have is bus mode, but that doesn't change. And then I'm not actually gonna have a state that is flush. Like, I'm not gonna wait for the flush to be done. The only thing I'm gonna wait for is issue the flush. So basically, my state machine is kind of connected to the command channel of the memory interface and not to the data path. So the data path kind of operates independently, because the memory controller allows you to queue several commands before it's done executing the previous one. So you can perfectly send a write command while the previous read command is actually still running and sending you data. That's perfectly valid. Yeah. And then once we have issued the flush, the next stage is going to be issue the load. And then we go back to bus mode. No. Because we've issued the command load, but before we can actually serve the request to the bus, we kind of need to wait until the load is actually done. We can't go back to bus mode and serving requests until the load is actually done and finished executing. And so we actually have a third state here. We wait for the load to be done, and then we go back to bus mode. So now one question that might not be entirely obvious is, okay, we wait for the load to complete, but we actually never wait for the flush to complete. Why? Like, why isn't that worth doing? The reason for that is okay. I'm just thinking about what's the best way to explain that. If we look at what's going to happen time-wise, so this is the command that are sent and accepted by the memory controller. We have flush. And then it's not going to accept any new command for a while. And then it's going to accept the command load. And then we're not actually sending anything. Now if we look at the write data channel, the actual data exchange is probably going to happen something like this. I mean, obviously, it's actually exchanging, several words of data, stuff like that. But what's important to see is that after the flush is issued, there is actually a gap here. That gap might be 0. It could be down to 0 actually. The controller is free to start consuming data as soon as it has accepted the write command. That doesn't matter. But what's important to see is that it will accept the next command before it's actually done executing here. So here you have an overlap, right? But something that is absolutely 100% certain is that the read data is going to show up obviously after the load command has been accepted, obviously. But the read data, this is always superior to 0, which means there is absolutely no way the memory controller could provide us read data before it's done accepting the write data. That just can't possibly happen because the memory interface is in order and it needs to have finished executing the write, and to have finished executing the write, it has obviously have to consume all the write data, and it can't possibly start providing us with read data before it's done consuming the write data. I hope that makes sense, which means that we don't actually need, we are absolutely sure that there is no conflict in accessing the single port RAM during the write and read period because there is no overlap between those two zones. And also we actually never need to wait for the write data to be over because all we need to do is wait for the read data to be done. And we know that the entire cycle is complete. The only interesting thing from the write data is at this point here, we're gonna reset our counter. So if you go back to the data path, this counter, we're gonna reset it. And that's why I said, reset the counter on write act last, is because once we've written the last data that we fetch, we reset the counter so that we're ready for the upcoming load data. Does that make sense? I hope so. And so I think design-wise, I think that's pretty much it. Which means, like, you see, the design of this part is actually like super simple. Like the connection from the memory interface to the SPRAM is pretty much directly connect. Like just wire things up. There's nothing. There is a counter which has some special condition to reset and some special condition to increment. And next to that, yeah, so from the, we need to generate the address, the length, and the read write, but the address, well, the MSB are the evicted tag. We have it, that's part of the signal that we discussed in the last stream and that we wrote the logic to generate. The middle part of the address, well, the LSB is zeros. Like we only access data aligned on cache line boundaries. And the middle part of the address, which is the cache line index, well, we know on which cache line we operate. That's part of the address that we latched. As I said, the length is done and the read write. And so the only signal that we need to generate is valid. And so valid is basically going to be 1 if we are in the issue flush or in the issue load state. And read write is going to be 1 or 0 depending on which state we're on. And we move on to the next state when ready is equal to 1. That's pretty much it. So we can actually just do that now. Let's just go to, yeah, let's go to this. I'm going to put that here. Now, that's always a kind of a question of where do you put stuff in a Verilog file, because everything executes at the same time, right? I usually try to keep like the pipeline from top to bottom, but here you kind of have two orthogonal things. You have like the bus access and the memory access, and they kind of orthogonal to each other, and they just interact using some of the RAM, which mean some of the elements, it's not clear where to put it. Can you increase the font size? Yes, I can try. That didn't do what I wanted to do. Is that better? Okay, great. So let's see. As I said, we issue command when we are in the state issue flash that... Okay, I didn't name them the same thing, but MEF issue, right? Okay, am I ready? That's an input, so we'll need it. In our state machine, actually. So we can. Basically, as soon as the memory interface is ready, that means that our command is accepted and we can just move on to the next one. When we wait for the memory interface, what we need to do is we're basically waiting for the last read data to come in. And so the last read data to come in, it's going to be these two signals. And when do we leave bus mode? It's if we have a lookup miss. Yeah. So we leave bus mode when we have a miss, and depending if what we're affecting is dirty or not. If it's dirty, we need to go there because we need to flush it. And if it's clean already, we can just load the cache line directly without flushing. There you go, that's our state machine. Like, that's pretty straightforward, right? There is no magic to it. Now, those signals are fairly fast and registered and everything, so that's not much of an issue. LU-miss is, you know, a pretty complicated signal that we evaluated last time, and we're combining it into state machine. That's definitely not ideal. Unfortunately, we don't really have a choice. And that's definitely going to be our critical path. Like, I pretty much knew already before starting that this was going to be it, and that's why I spent so much time thinking about the logic in the previous stream. Is because I knew that this particular signal, not only computing it was, you know, was going to take quite a few layers of logic. I think it takes 6 layers of logic to compute it. But I was going to use it to combine it with as an input to a state machine, which is going to add, you know, inevitably a couple of layers of logic as well. I'm hoping that this won't increase it too much. We'll find out. Now, of course, if you only have, one signal that's slightly longer than what you would want, most of the time it's not that bad, because if you have very few signals that are longer, um, next PNR is going to be able to place them, uh, closer to each other and reduce the routing delay. If there is very few critical signal, it will have the flexibility to do that. If you have a lot of paths that are very long, well then, it can't place everything close together, so you have limitation. But if you only have one path that's slightly longer than what you would like, it's most often okay. So we have the address. So as we said, the address is composed of the tag that we're evicting. Wait. Will that state machine get turned into a mux? I mean, that state machine is going to use the current state is used to drive some of the muxes. So last stream we took a quick look, at the SPRAM address and some of the shade block, what the inputs were needed when it was in bus mode or when it was in memory access mode. And so the current state is going to be used to drive those muxes. And you have an example of that here at the bottom. So that'd be an example of the muxes. That's all the DM signal that drives the data memory, and so that's basically the input to the SPRAM. And so if we were in bus mode, so this is just a comparator that checks if the state is equal to ST bus mode or not. If we're in bus mode, it does some kind of access, and if we're not in bus mode, that means that we're in memory access mode, then it drives the signal differently, basically. But all of that is driven by the current state of the state machine, and the current state is a register. It's a state register, which means it's a fast signal. And here, that's the logic that generates the input of that state register. So basically the way the state machine in this case work is we have a register that stored what I call CTRL state, and this is used to drive all the control mux, and then you have a feedback, and then you have a bunch of next state logic that computes the state of the state machine for the next state, and this takes inputs from the rest of the design, basically. There is one path that actually goes out of here and controls the clock enable of a register, which I honestly don't like that much, because usually I like to have the next state logic only drive the register just for timing purposes. But here I just needed that signal somewhere else. We can take a quick look at it. So where is it? Yeah, it's here. it's just a way to save a register that I mentioned in the last stream, that I could save a mux and save a register if I only updated that register when we're in bus mode. It turns out that it's not when I'm in bus mode or not that I need to enable that register or not. It's if the next state is bus mode or not. And the next state is the output of that logic, which means, yeah, I have to test it. If that turns out to be an issue, I can change that, but I don't expect that it will be in the critical path. Because again, the clock enable of a register is a pretty fast input. Like, it doesn't have much time, setup time. Does that answer your question? Why are you swapping hard drive? Well, first, why do you still have hard drives? Move on to SSDs. You rarely use equal. Well, you need to use. You mean here? It's because this is a combinatorial process. Every time you have a combinatorial process with at star, you need to use equal and not the other one. One is the blocking assignment, the other is the non-blocking assignment, but I don't remember which is which. I think this is the non-blocking assignment and this is the blocking assignment. And so you need to use this if it's a combinatorial process, and you need to use this if it's a clocked process. Okay, you're installing SSD. Yeah, that's a good reason. Actually, completely unrelated to what I was discussing before, but just because I have it on the screen here, something you'll notice here is that I have always at pos edge clock or pos edge reset. So that's used to create an asynchronous reset. And the reason I'm doing this on every flip-flop that I have a reset on this design is because on the iCE40 FPGA, if you have a flip-flop with a clock enable and a reset line, the clock enable has priority. So if you have a reset set to 1 and clock enable set to 0, your flip-flop won't reset, and that's just not configurable. And that's kind of unusual. Usually the reset wins, the reset has priority. But that's only if the reset is synchronous. And if you move to asynchronous reset, then you don't have these issues. And then sometimes that helps pack the logic better. So that's kind of my advice on iCE40 is use asynchronous resets on your flip-flops. Anyway, that was just a small digression. What was I doing? I was coding the commands. Okay. So the address, the address I'm sending, it's kind of depends of the state, right? Because if if I'm sending a write, that means I'm flushing a thank you, DH73. So yeah, that's what I was that's what I was thinking. So the blocking one is the equal one, and the other one is the non-blocking one is the small arrow. And so you use the non-blocking for clocked process and the blocking ones for combinatorial process. That's like the rule of thumb which makes things work. There is an explanation of exactly what can happen if you don't follow that, and it can basically yield like non-deterministic outputs, especially in simulation. I mean, like different tools will have different interpretation. But so yeah, basically just follow the rule of thumb, and that works fine. So the address of the command. If we're issuing a write, that means that we're flushing a dirty cache line back to memory. We need to use the tag of the dirty cache line, which we're evicting. And if we're issuing a read, we basically need to load the tagline. So that's the, oh wait, what? Yeah. Tag the that's always the index of the that's the index of the cache line. That's always the one from the request, and that leaves us with the offset inside the cache line, which is always 0, and so this is just off with okay, that's the address. The length, as I said, that's just always cache line, okay. Actually, that's cache line divided by 4. The cache line is in bytes. Actually, that's cache line divided by 4 minus 1. So yeah, because the length field is in words, not in bytes, and it's 0 is 1 is one transfer. Invalid, and then we have assign mi rw. Issue. So that signal, the read write is 1 for read, and 0 for write. So that's the command, and the other thing that we had in our design is that famous counter. Well, we can connect. So I'd already connected the. So this connection here. Okay, yeah. This connection here, I already made it here. Here, sorry. So the write data of the SPRAM is already connected to the read data, and the write enable is already connected to the read strobe. So that connection I've already made. I just need to make that connection, and then the whole counter thing still needs to be done. Because you see here in the code, I just put fix me, which is not obviously not gonna work. So I am going to need a counter. That counter is going to be this wide. What am I gonna? What the hell? Yeah, so just taking care of the spam. So I need a counter for the offsets. I'm gonna call that counter offsets. Damn it. So I have this counter with two control signals, one to reset it, one to increment it. I can use it now. So now I just need to generate those signals. Where was I? Oh yeah. So as I said, I need to reset it on cache miss. Not a miss signal itself is actually pretty. You know what? I don't need to reset it on cache miss. I can just reset it all the time while I'm in bus mode. So I can just, because that counter isn't used in bus mode, and I will always go back to bus mode between two memory interface commands, which means I can just reset it while I'm in bus mode. And the other way to reset it is if I'm write ACK last, and so that's mi write ACK and mi write last. So that was easy. So when do I increment it? Well, that's a little more complicated, mostly because of the. Here we have a read pipeline, like we have a register here, we have a register here, which means that we need to kind of prime that pipeline. Hey, no problem, Matthew. Yeah, see you later. Thanks for joining. I'm gonna like stop in like 15 or 20 minutes anyway, because I need to sleep, and once I'm done coding that counter, I'll just probably just close up, so you won't miss much. You won't have much to catch up on. Yeah, so that read pipeline, we need to prime it. Kind of like when you start a pump, which means that before we get the first acknowledge, we actually need at least one cycle of read enable just to like bootstrap it. And so we're just gonna use the cycle in which the read command is accepted, basically. So we need, well, first, yeah, so we need to increment it when we have a ACK from the right side, or when we have a hack from the read. Wait, no, this hack, and then when we actually prime it, and the priming is when am I ready, and issue. So when we issue the write command and it's accepted because the memory interface is ready, then we will issue a single read cycle. We will force that signal to be 1, so that this goes from 0 to 1, and the SPRAM actually reads one data, so that this becomes valid, basically. And so that signal is the same as the read enable. So if you, I'm kind of cheating here because this will actually be 1 as well during when there is a write strobe here. When there's a read strobe here, wait, I have 2 mouse cursor. So that signal will be 1 when there's a read strobe here. But it doesn't matter because the read enable is only used to force the chip select of the SPRAM, and the chip select is forced by this anyway, so yeah. Do we have any fixed me left in this? No, so I think that's actually connected. That's connected. Sort of this is good and complete. That's good. So this is left to do. So I did. So these are all the write signal to the tag memory when we need to update it. That's something I haven't done yet. I do have the signals defined here already. Well, first let me check if it's actually built, just to make sure that I just want to feed all the files to iVerilog, mostly just to make sure that I don't have any like syntax error or stuff like that at the moment. Okay, yes. So I misnamed some signal or something like this. So let's just fix that up quickly. Yeah, it's not state, it's control state. Yeah, same here. See, that's why it's really important to use default net type known. It's to find those typos. Okay, so I think is there might be a warning old flag or something. Oh wow. That's a lot of warning. Yeah, so the that doesn't matter. Instantiating MCM with dangling input port 2. Yeah, that's the all the unconnected signal that I haven't connected yet, so that's kind of expected. So I can connect these. So I'm just wiring up the tag RAM. I will worry about actually generating those signal later. Wait, what did I do here? Yeah, so I mean that's just wiring those things to the appropriate port. That's really not fascinating stuff. Every of yeah, pretty much all of those signals we discussed in the previous stream. Like if we look at this, we discussed, you know, what those signals must be in the different modes. So it's really just writing the Verilog for that. So I think actually I will end here because this is just gonna be tedious. Just clicking the port, and we're coming up on 2 hours of streaming, so that's and midnight here, so that's a pretty good stopping point. So if anyone has any question or something that wasn't clear or that you would like explain or anything like that, please ask in the chat now. And if not, well, thank you all for joining. I hope it was interesting. I will just finish wiring that up according to the diagrams that we made the last stream. And actually, I think that once that's wired up, I think we're actually done. Because I don't have any fix me left. So for the next stream, I will try to write. At the moment, I don't have. I only have a real memory controller, which is kind of hard to simulate because you have to simulate all the I/O delays and the blocks of stuff. I will just write like a fake memory controller that has the same interface but loads data from a file or something, so that we can try to connect the cache to that fake memory controller and just send some artificial requests to it from the test bench and see how it reacts, basically. Because I mean, when I say we, it's more like me. I undoubtedly fucked up something somewhere, and so simulation will definitely be useful to at least get it to a point. Yeah, where it has a chance of working. So something that's still missing is that like the interface here, like the request input, that's not Wishbone at all, right? That's like a custom interface thing. That's just like the natural fit for the design I came up with. But this still needs to be adapted to Wishbone so that we can connect it to any peripheral, and so I will write. I named this MC core, so like memory controller core. I will write like a Wishbone bus adapter, and I will also later, once it works with Wishbone, I will also write PyCore RV adapter so that it connects slightly more tightly with the PyCore RV, and probably a VEX adapter as well, so that I can connect it to a VEX CPU more efficiently than just using plain old Wishbone for everything. So yeah, there is still some work to be done for sure. Yeah, the block RAMs in the iCE40 are definitely weird. Yeah, so well for your first question, the block RAM is definitely weird, and I'm actually wondering if it's not because if you do I don't know how users handles read and write conflicts to the same address basically. As far as I can tell, it doesn't generate any special logic, and it just assumes that the block RAMs is read before write. But at least according to the doc and to the simulation model, that's not gonna work. I would be curious to test in hardware how the hardware actually behaves. Um, does it behave as read after write, or does it behave as something else? Is it random? Can it corrupt data? That kind of stuff. Because um, I could definitely see um, read and write to the same address happen in some design, and if Yosis doesn't isn't aware that this is undefined behavior, it could generate logic that doesn't actually work, which is definitely not good. Um, so yeah, that's probably something worth investigating. Yeah, I mean the Vex. Um, actually, we can have a quick look at this, but uh, where is this thing? So the Vex is not natively wishbone. You kind of take the native bus of the Vex and convert it to wishbone, and that's how it's used in Lytix, because in Lytix everything is wishbone, and so they just convert it to wishbone. But you have other plugins where you, instead of wishbone, you can actually get other types of buses, including other bus type which are much more efficient at transferring data than Wishbone. For the data bus, I'd probably stay with Wishbone, or maybe it's actually worth changing as well. Um, but at least for the instruction bus, you can get like pipeline bus access and that kind of stuff, which is much faster, especially if you have an if you use a layer one cache, a level one cache inside the Vex, you can get burst access so that the level one cache of the Vex would load entire cache line um, from the layer 2 cache basically that we're designing now. And as I said, the Vex is, and the PyCurve as well, is heavily memory bound. Like, that's actually something you can do pretty easily. If you on the PyCurve, you can enable or disable, for instance, the compressed instruction set. So RISC-V instruction, they're 32 bits, but there is also the compressed instruction, which are only 16 bits, kind of like the thumb mode of ARM, but for RISC-V. And using compressed instruction, you can actually get a lot of performance gain just because in a single word fetch, it actually can fetch 2 instructions, and so it's not waiting as much for memory, which is something interesting. Yeah, okay. I think that's it. As usual, for you can subscribe either to Twitch or on YouTube if you want to watch the recording. I will upload the recording to YouTube as well on my channel. If you want to find me to ask a question or anything, you can find me on the I close the tab, of course, but I think it's 1bitsquared.com/chat. Nope. Pages/chat. Yeah. I hang out on that chat all the time on the TNT or on a Freenode in the Open FPGA channel. You can find me there as well. If you have any comment, question, or anything, or feedback or whatever, yeah, there you go. Piotr pasted the link on in the chat. And yeah, that's about it. Thank you everyone for joining, and see you next time, I guess. Bye.